Okay, it's really a pleasure to be here, and I mean, it's. I would like to thank all the organizers for inviting me over and giving me the opportunity to visit again Japan. I I was in Japan 3 times in the last 30 years, so it's approximately once every 10 years. Maybe I will try to make it more often in the next few years because it's always great. Okay, so this is about some work I've been doing on topics that concern regret analysis in digital markets. There is a little bit of wordplay. I mean, of irony in tariffs. It's not going to be on tariffs, but although some applications can be viewed as applications on tariffs. Yeah. Okay. So right. So let me. There is a little bit of a research agenda here, where in long learning you all know you have algorithms that interact with environments in a series of rounds. That's the basic setting. And so in each round, the algorithm will make some decision, will receive some utility, and will get some feedback. Where utility is typically something that is not necessarily observed, whereas feedback is, by definition, is observed. So the goal is to use each feedback to optimize the future utility, and what determines the optimal learning rate. So the way we can exploit the feedback as much as possible to increase utility is the interplay between the structure of the decision set, the shape of the utility function, and the type of feedback, and also the type of environment. All these factors, all these features, contribute to determine what is the best possible learning rate. And the challenge here is to find some simple algorithm that is able to exploit the feedback information in this optimal way. And this is a little bit the kind of game that I guess we all play when we do online learning. So in this context, the digital markets are a very nice playground because they provide very many problems that are by definition interesting because involve a lot of money in general. So this is and they are typically non-trivial because the mechanisms that operate markets are subtle, are not trivial, and they also provide very many types of decision spaces and feedback and so on. So there's a big variety of problems down there. And so I've been interested in this since the last maybe 15 years. Okay, so let me just review, for the sake of terminology, what we mean by sequential decision making with partial feedback. Typically have K actions and some unknown deterministic assignment of revenues to actions. I will be working in a non-stochastic setting mostly, although some of the results will be for the stochastic setting. So actually, the assignment will be deterministic, but maybe stochastic, in which case I will make it clear. All right. So there's going to be assignments of revenues to actions. So revenues are bounded in between 0 and 1. So at every time step t, we have some known vector of revenues, and the algorithm will typically use randomization to pick an action according to some distribution qt over the action. We'll get some hidden revenue, the revenue of the chosen action, and then the player will observe some feedback information, which typically depends on the randomized action. So the feedback itself is a random variable because it's a function of the action, which is a random variable. Okay, so this is the general setting. So we we all know and love regret as a measure of performance in this kind of settings, where we compare the total revenue of the best action in our set of K actions with the player's expected total revenue, which is the sum of revenues accumulated by the player over a sequence of T rounds. So, and we would like to minimize this difference. So we'd like the player to be as close as possible to the revenue of the best actions, irrespective of the sequence of revenue vectors. Okay, so expectation, of course, unless specified, will be only with respect to the player's internal randomization, because the environment is deterministic, adversarial, if you like. And since everything is bounded here, it's very easy to get a big O of T regret. You just play at random. The regret cannot grow any faster than linear. So the goal here is to ensure that the regret will go sublinear over time for any sequence of revenues. Okay, so QT is again the distribution of players' choice, time T based on past feedbacks. And so we can also write, so this is essentially, we can write the expectation as a linear operator. So the expected revenue with respect to distribution QT is the inner product between the revenue vector and the distribution, which we see as a vector. And then what we typically use as a player's algorithm is follow the regularized leader, which is a general workhorse for online learning. And here is a maximization because we want to maximize revenue. So we will predict by maximizing the sum of past revenues with respect to all distributions in the simplex here, in the simplex over the K actions. But we will regularize this using a strongly convex regularizer phi, which may also depend on time. Okay, so, and we all know that if we have a full information here, so if at the end of each round we are actually able to see the entire revenue vector, then by using a entropic regularizer over here, we will be able, follow the regularized leader will deliver an optimal regret rate. Well, this is actually optimal, not up to log factor, but this is, this is actually optimal including constants, because we can prove asymptotic lower bounds that have these exact constants. Okay, so square root of T and the logarithmic dependence on K is the best possible regret rate in the full information case. But in most of the applications of digital markets, you don't have this full information. You cannot afford the full information, but you have only partial feedback. So, so typically, we will use this variant of follow the regularized reader, which is known as XP3, and this is for the case of bandits when your feedback is only the revenue. Okay, we will see that in some of the applications this is not the case. You have a slightly altered bandit feedback, but in general, in the bandit case, we all know that what you observe is the revenue of the action you picked and nothing else. So in this case, you can still use your follow the regularized leader algorithm and with the entropic regularization. And there's specific randomized revenue estimates that are, that are constructed using importance weighted techniques. And the combining this, there is a very standard analysis by now that delivers the upper bound of the regret, which depends on a bias term, the log of the number of the actions, and the variance term, where the variance will depend on your revenue estimates. Okay, the squared of the revenue estimates. Okay, this variance, because we are using FTRL with entropic regularization, and especially these randomized revenue estimates, can be bounded with the number of actions. So then by choosing suitably the learning rate eta, which is the learning rate that is attached to the regularization, we can upper bound the regret with this quantity over here. Okay? And if you want to be a little bit more careful, we can use a special kind of entropy, Zallis entropy, as a regularizer, and this will actually deliver the optimal regret rate up to constants, which doesn't have this log k. However, here we are not so much interested in logarithmic terms, so both of these we will especially be interested in using entropic regularization. But we know that we can get optimal bounds using this slightly different regularizer. Okay, so again, you see these are basically the leading rate. So square root of kt is the rate that you would expect when you play a bandit over k actions in a non-stochastic environment. And this algorithm will be, and this bound will be our main tool here when we apply this machinery to digital markets. So let's look a little bit of what's going on here. So here we have a typically high volume stream of trades where buyers and sellers are algorithms, and they engage in trading according to some kind of market. And typically everything is algorithmic here, so you have millions of trades per day. So your decisions typically will be prices, and we will abstract the granularity of the price by considering a continuous bounded price range in the unit interval. And your goal the goal of typically is to maximize revenue in a sequence of trades, which in our jargon means that we want to minimize regret with respect to the revenue of the best fixed price. Okay, so in these applications, we will look at a single agent problem. So there is only one strategic agent, the algorithm, and everything else is the environment will be adversarial. There are no other strategic players besides the algorithm. Okay, so yeah. So as I said, we have, in order to get optimal rates, we have to exploit the structure of the feedback in order to control the variance of the revenue estimates. So if you remember, we have this bias variance trade-off. The bias is the bias, and we can design revenue estimates in order to control the variance as much as possible. And this will be the name of the game in this setting. Okay? So how the feedback structure enables us to control the variance of the revenue estimates. All right, so we have a bunch of, so there were a few landmark papers, like the paper by Kleinberg and Layton 12 years ago, and posted 22 years ago, but on posted price auctions. And this here is a little bit of a selection of papers I've been working on in the last 8 years, and there's a few more in my group and with my co-authors, but I will be mentioning primarily these ones, at least some of them. Okay, so you see there's quite a variety of problem that can be solved using these tools in digital markets. Okay, so at the end of the day, there's a number of recurring themes, okay? A number of recurring themes when you go about solving a problem like this using bandits. All right, so let's start with posted price auctions. And one of the themes or features that will appear here is the one-sided Lipschitzness of the revenue function. So this is a first structural property that we can build upon to get a good variance bound for our revenue estimates. So here what happens, so there's a customer arriving with a private evaluation for a certain good. Okay, so he wants to buy a t-shirt on your website, and the website will post the price to the customer, and there will be a dynamic pricing policy. So every customer may receive a potentially different price from previous customers. Okay, so the idea here is that if the posted price is smaller than the valuation of the private valuation of the customer will buy the good. However, we will never get to see the valuation, the private valuation of the customer. The only thing we get to see is whether the customer bought or not. And the buying will always happen at the price we posted. So there's no other information. We know that either he bought it at that price or he walked away. All right, so we can now plot the seller's revenue, which is that simple formula over here, as a function of the posted price, and parameterized by the valuation of the customer. So you see, the revenue will grow linearly as we approach the valuation of the customer, and then will drop to zero if the posted price is above the valuation of the customer, because in that case, the customer walks away without buying. Okay, so this is the utility function. That's the feedback. The decision space is the unit interval. So these are our ingredients. And we are going to, the valuation remains unknown, and the regret will be defined with respect to the best price revenue in the continuous unit interval. Okay, so we want to compete against the best price in the 0-1 interval. Okay, so what can we observe here is that the revenue function satisfies this property, which one-sided Lipschitzness, which means essentially is that as we walk from left to right, the function is not going to grow any faster than the straight line with coefficient 1. Okay, so actually it will drop, but will definitely not go faster than this, moving from left to right. That's why one-sided Lipschitzness. And this property is crucial because it allows us to discretize prices by incurring a fixed approximation cost. So this is super, super easy. So we can go and discretize prices on a grid with epsilon. At this point, we can get our regret, and we can decompose the regret in a bandit error, this term over here, which is competing on the best price over the grid, okay, plus the approximation error, which is the error we incur because we approximate prices on a grid. So we play on a grid, and then we trade off with the approximation error, okay? So everything becomes pretty easy because the one-sided Lipschitzness tells us that essentially if we choose the binning of the grid in the right way, so we play the prices on the left-hand side of each bin, we can exploit this one-sided Lipschitzness, and we know that we are going to incur an approximation error of at most epsilon at every round because we play a price which will be our optimal price on the grid will be at most epsilon smaller than the best price, okay? Than the optimal price on the unit interval, okay? So there will be a bin containing the optimal price, and we play the price on the left-hand side, and therefore we incur of that bin, therefore we incur that approximation error, which summed over capital T rounds will sum up to epsilon T. So we have 1 over epsilon actions, and then we can apply our optimal bandit algorithm and get this kind of bound over here. Everything is fine. Now, the revenue, the variance of revenue estimates, because we are in the standard bandits, will be K. You remember the variance in bandits is bounded by K. Here, K is 1 over epsilon. Everything is fine. So we get some approximation error, some bandit error, and we write them in terms of epsilon. We tune epsilon, and we get the T to the 2/3, and this is an optimal bound up to constants, factors. Okay? So this was pretty easy to solve. We just used our standard machinery. We had this nice property, one-sided Lipschitzness, and we could obtain this bound over here. Okay, so now let's move to any questions up to here?
Thank you for your great talk. Is the problem related to partial monitoring?
To what?
To partial monitoring.
Partial monitoring, yeah. It is a problem related to partial monitoring, and partial monitoring is a more general and abstract model that includes all these things I'm going to talk about in the rest of the talk as special cases. Okay, so the thing is that partial monitoring typically has, first of all, bounds are not completely interpretable. And secondly, the algorithms may be not efficient. And thirdly, it's not always possible to deal with continuous decision spaces. So I could use partial monitoring, but I would end up with algorithms that are complicated, bounds that are not easy to read, and sometimes I wouldn't be able to do it because I'm using variants that are not covered by partial monitoring. But in principle, yes, these are all instances of partial monitoring. Okay, let me move to the next example. So second price auctions with reserve price. And now we are getting another property at play here. Besides one-side Lipschitzness, we will have one-side observability. Okay, so there is another feature of the bound, of the problem that allows us to solve the bound in a different way. So let me explain it. So these are second price auctions. We have a seller. The algorithm will be a seller in an auction, and the algorithm will choose the reserve price. Okay, so what happens here? So the seller will choose a reserve price, and simultaneously bids will be submitted. Okay. So buyers will submit bids, and then what happens? So in an auction, the reserve price is the smallest price at which you're willing to sell your good. So if the highest bid is below the reserve price, then you're not selling anything. And this is this part here of the graph. Okay, where, this is like on the x-axis are the reserve prices. This is the highest bid, and this is the second highest bid. So if the reserve price is bigger than the highest bid, no auction is carried out. Okay? Otherwise, the winning bidder will get the good and will pay the maximum between the second highest bid and the reserve price. Okay? So now there are two cases. Either the reserve price is smaller than the second highest bid, in which case the winner will pay the second highest bid, or the reserve is in between the highest and second highest bid, in which case the winner will pay the reserve price. So in this game, the seller wants to put a reserve price between the highest and second highest bids. However, we don't know these bids, and these bids will come adversarially. Okay? So there's adversarial sequence of bids. We don't know anything about these bids. We don't know the process generating these bids, just like we didn't know the process generating the devaluations in the previous case, but we want to maximize this revenue over here. Okay? So our feedback in this case will be the revenue and the winning bid. So we'll be told which was the winning bid, and we will be told whether our revenue is the second highest or is the reserve price or nothing. Okay? So now this function again is a one-sided Lipschitz function. You can see it, you know, because it doesn't grow too fast, moving left to right. But also you have this other very important property. The feedback allows the seller to compute the revenue of reserve prices that are bigger than the reserve price played by the algorithm. So let's reason about this. Okay, suppose that I play a reserve price over here, then my revenue is going to be the second highest bid. I know the second highest bid at this point, but I also observe the winning bid. Okay, because that's the feedback. So now, if my reserve price happens to be here, I will know B2 and B1, so I can reconstruct the entire revenue function, and therefore I will know the revenue of all other prices, not only those that are bigger than the price I paid, but all the other prices. Okay. Second case, if I play a price in between here, the revenue will be the price I played, but I will also observe the winning bid. So basically, suppose that I played 0.6, I will know that B1, the highest bid, was 0.7, and therefore I can reconstruct the function from here onward. And therefore I know that I can compute the revenue of all the prices that are bigger than the reserve price I did play at this round. Third case, I play a reserve price over here, my revenue is 0, and then I know that any bigger reserve price would have gotten the same revenue. Okay? So this is one-sided observability. It's a feature of the feedback in conjunction with the shape of the reward function. So now I can exploit this thing, and I will proceed as before. I will discretize prices because I have a one-sided Lipschitzness. I can decompose regret into bandit error and approximation error. I will use one-sided Lipschitzness to bound approximation error. And I will now run XP3 over, again, 1 over epsilon, where epsilon is the size of the discretization. However, the way I exploit this one-sided observability is the following. I will add a small probability gamma of playing a zero reserve. So since I always observe everything, I always observe everything that happens on the right-hand side of the price I play. In order to get full information, occasionally, with small probability, I play a reserve price 0. This, by definition, allows me to reconstruct the entire revenue function, so I have the full information. But I pay because my reserve price is 0, so I don't gain, I only gain the second highest bid. I never gain anything in this region. So it's a costly exploration that allows me to get full information feedback. And I tune the probability of doing this, okay. I tune this probability so that to get a good bound. So now I have the same thing, the bias. I have the bias, the variance. Now, because I'm using a different estimator, the variance will be bounded this way. So you see, this is the one-sided observability, and the fact that I'm using this probability of playing a zero reserve allows me to get the bound on on the variance of the estimator, which is the log of essentially of E over gamma, where gamma is this probability of exploration. So this is a pretty good bound on the variance. It's much better than the bound on the bandits, which was 1 over epsilon. And then I have an exploration cost, because with probability gamma, I'm going to play a zero reserve, which is typically suboptimal. So we'll pay this additional cost. So now I can do a tuning of all these terms. Okay, I have k is 1 over epsilon, and then I have everything else, and it boils down to a regret, which is square root of t up to logarithmic factors. This regret is full information. Okay, remember the full information is square root of t. There is no k anymore because k is 1 over epsilon, and I did the tune 1 over epsilon, right? And I have this full information rate. So Lipschitz, one-sided Lipschitzness plus one-sided observability in these particular problems guarantees a full information rate, which is kind of interesting. Okay. Yes. Can you repeat?
Is it an assumption that you observe the highest bit?
It is an assumption. It used to be true in some big ad exchanges. So this used to be advertisements were sold using second price options until a few years ago. Now most ad exchanges switched to first price options. Okay, so when we did this research, it used to be true that the advertiser was told the highest bid. Yeah. Okay. So let's say it's an assumption, but it is a reasonable assumption, which may happen in practice.
Okay, thanks.
Question.
Yeah.
This second problem seems more difficult than the first one, but the regret bound is better. Can you explain why?
No, it's actually not more difficult because the previous problem had one-sided Lipschitzness. This one has one-sided Lipschitzness plus one-sided observability. So you have two properties to build upon. So in this sense, it's easier. Okay. It's not harder. Okay, because you have these two properties, which are good properties. There are also bad properties. It's true, but in this case, these two properties are good. Okay, more questions? Yes, Mike.
So for me, it seems like with that gamma of exploiting everything, you get a nice bound for that variance term, right? So yeah. Is there like an intuitive explanation why using that information helps us in the future? Yeah.
Okay, so basically prices are ordered, right? So you always get the okay. So remember that the variance. Okay, here's the variance. Good. So the variance is the sum over all the prices. In this case, discretized prices of these things over here. So now, because right, you need these revenue estimates, but in this case, you right. Let's see. It's kind of intuitive that if you can compute the revenue of things you didn't play, that's better. Because if full information is the best possible case, and in full information you can compute the revenues of all the prices, even those for all the prices that you didn't play, plus the price you did play. In this case, you can compute all the revenue of all the prices bigger than the price you played. Okay, so if you tend to play in the middle, then you will know the revenue of half of all the prices. So it's kind of a half a full information. So now you're saying, okay, you know, sometimes I will play at the beginning, so I see everything. So I am full information with some probability. And then it's just a matter of, so the computation of this variance term is actually a nice sum. as a sum that you upper bound with an integral, and the integral boils down to this log E over gamma. And it's actually because you always see the bigger prices. So you can do a sum. So there's a nice sum that pops up when you're computing this variance. So that's the kind of idea. So you always you always have the information for the bigger prices, and if you play small, then you see a lot. But you cannot play small too often because otherwise you lose. Okay? Cool. All right. Now, let's move on to another. Okay, this is harder than the second price. So this is first price auctions with unknown valuations. So this is something, first price auctions is now things that are used typically to sell advertisements. And so there's a buyer, and we are on the buyer side in this case. We are not on the seller side. So we are the buyer. There are other buyers, and we want to get some good. So we will make a bid, and the maximum bid, the maximum of the other bids will be revealed. And if our bid is bigger than the maximum of the other bids, then we get the good. Okay. And however, the buyer's valuation V is revealed only if the action is won. So this means that essentially we don't know exactly how valuable is the good that we are bidding on. It's like, suppose it's an advertisement. We don't know how much this advertisement will be worth for us, but we bid something. If we win it, then we will know how much was worth. Okay? If we don't win it, we never know. Okay, so that's the idea. And the regret is measured with respect to this revenue. So the revenue is the valuation minus our bid, which is how much we get if we win. If we win, we get the valuation minus our bid, because we have to pay the bid. Okay? But this only happens when the when the bid is bigger than the largest, highest competing bid. Okay? And these are the revenue functions according to whether the maximum valuation is below our valuation. Sorry, the maximum bid is below our valuation, or vice versa. And these are nasty functions because there is no one-sided Lipschitz. Depending on whether we are here or here, the function has a different behavior. But we do have one-sided observability. Feedback allows the seller to compute revenue of bids that are smaller than the bid that we made. I'm not running into the exercise. You can check it yourself at some point. I'm not doing this exercise, but you should be convinced that in this case, you have, because the maximum among the remaining bids is revealed, which means that if we lose the auction, we are told, oh, you lost the auction because this guy bid larger than you. Okay? So it allows you to compute the revenue of bids that are smaller than the one you played. Okay? So now we don't have this other property, but we do have this one. So what's going to be the optimal rate here? Okay, so it turns out that we have to, we cannot really prove a sublinear upper bound on the regret under these conditions. The problem here is that because we don't have a one-sided Lipschitz, we cannot discretize. And if we cannot discretize, the adversary can play real numbers on the line and can play these real numbers in a way that forces us to have a linear regret. So there's nothing we can do here, but we can play a trick. We can move to a smoothed adversary. So we inject a little bit of randomness. This means essentially that the adversary cannot pick. So the adversary typically will pick MT and VT. These are two numbers picked at the adversary. But we don't allow the adversary to pick these numbers exactly as two real numbers with infinite precision. we inject some randomness so the adversary can pick these two numbers, MT and VT, up to some variance. Okay? So this is called the smoothed analysis. And we are saying that, yeah, essentially, we are going to have some sigma term which measures the smoothness. If sigma is 0, we are back in the adversarial setting. If sigma is 1, then we are in the stochastic setting. Okay. So now we assume that at each round t, the maximum bid MT and the Bayer evaluation VT are jointly drawn from a sigma smooth distribution which can vary with time. So the adversary will choose mu t, but mu t will determine MT and VT up to this sigma parameter. Okay. Okay. What we gain here is that the expected revenue becomes Lipschitz. Becomes a Lipschitz function. And so therefore we can discretize. So smoothness is a trick that allows us to have the revenue Lipschitz in expectation with respect to this randomization in the environment. Okay, so now what we can do here, we can do as before. So we discretize, but we also have one-sided observability. So we add a small probability of bidding the maximum bid. Why the maximum bid? Because if we play the maximum bid, we always get the object. So we always see the evaluation of the object, and we always see what was the largest bid. So we have a full information if we bid 1. Okay, so this is again an example of exploiting one-sided observability with the small probability because we pay. We make an exploration, but we pay also. Okay, so again, we're going to have our bias, our variance, our exploration cost because of the gamma, and now the variance because of the structure of the estimator here is going to be bounded by 1. The way why this is bounded by 1 again is a bit complicated thing. Is the way we construct this estimator. It becomes a bit too complicated to explain it, but trust me, you can design an estimator which is unbiased for the revenues and has a variance bounded by 1. And at this point, you can do your tuning. You put all these terms and you tune them, and you get something which is, it depends on 1 over sigma, because the sigma equals 0 recovers the adversarial setting, but I told you that in the adversarial setting you have linear regret, and indeed 1 over 0 is infinity, so your regret blows up. Your regret bound blows up. But if sigma is finite, then you get something which is ln square root of t, which is a pretty reasonable rate in this problem. So here is a trick where we can compensate for the lack of Lipschitzness using this smoothing assumption. Okay, let me do this, maybe this last example, and then I will wrap up. So this is the latest paper, which was, yes, you have a question.
I was curious if there might be some way like where you can actually change the auction so that you can realize the smooth adversary assumption. Like I guess for NT, if you automatically added noise to that, that's fine. But for the valuation, I don't know.
Yeah.
For VT, like.
Yeah. Yeah. I understand. Yes. Okay. Actually, let me see. No, I think. I mean, there are so many settings in the sense. I think here you might need the smoothing only on one of these two variables. Might be the case.
Like 1 might be enough.
Yeah, yeah, yeah. But one of the two has to be specifically one of the two, not either one. So right, I don't remember exactly here, but yeah, that's true. So. Anyway, smoothing seems something reasonable in the sense because there's always some kind of, I mean, yeah, it's a good way of parameterizing your adversary. Okay. Yeah, thanks.
Thanks.
Okay, let's move on to the last one. Right, this is a trading. So we are market makers, and there's traders are arriving with some private valuation for some asset, and we post an ask and a bid price for that asset, and okay, and if the valuation of the trader is smaller than the bid, then we are buying from the trader. If the valuation of the trader is larger than the ask price, then we sell to the trader. If the valuation is in between the bid and ask, then no deal will take place. Okay, so this is a standard trading model. And here, V will be a adversarial quantity, but we also have another adversarial quantity, which is market price. So you can assume that you can always offload your inventory to another market, which will always buy it at the market price PT. So either you will get cash or you will get an asset which you can always sell to another market with infinite liquidity and a market price PT. Okay, and so the idea is that you will make some deal. If the deal happens, you will earn something, and the amount that you earn depends on the market price. And the feedback here is the direction of trade. So the only thing that you get to know is whether the trader bought or sold, whether you bought or sold. But you don't get to see anything else. And in particular, you don't, but you also get to see your revenue, because, no, you don't get to see the revenue. You get to see the market price, but your revenue will depend, oh, no. You get to see your revenue, sorry. You get to see your revenue as well, because PT is PT is the market price which you see, and B and A are your actions, okay? And you know the direction of trade. You know whether this was true or you know whether this was true, but you never get to see VT. Okay, so this is interesting because it's a kind of articulated model. You see, you have this. The revenue function is composed by these two parts because you have either a buyer or a sell. And that's the function over here. So the observation here, so this is a nice property. So this part over here, it's actually the revenue function of a first price auction with bid B and unknown valuation PT and highest competing bid VT. So you can formally view this part as a first price auction like the one we had in the previous model with unknown valuation. Oh, that's interesting, so fine. The second part, which is this one over here, is the revenue function of a posted price auction with price A unknown, with price A, unknown valuation VT, and production cost PT. So it's slight variation of a posted price auction where you have some manufacturing cost for selling your good, okay, before you sell your good. So now you can use the two algorithms we saw before, the one for posted price auctions and the one for first price auction, dynamic pricing at first price, to solve this problem. And the way you do it is that the following: you run in parallel a first price auction bidder and the posted price auction seller, and the bidder in first price will get you the bid price, and the seller in posted price will get you the ask price. And then what you do is that if BT is smaller than AT, then you will post the bid ask that the two algorithms gave you, and otherwise you swap them. If they are in the wrong order, you swap them, and you will post that pair. So, and then you relay the feedback to both instances of this algorithm, as the swap did not happen, and the feedback will be enough to run both algorithms, in the setting I told you before. And the crucial property here is when you flip, you are actually increasing the maker's utility. So swapping it's never hurts, okay? Because these two algorithms are run independently, so they don't know, each one doesn't know how big is the BT and the AT, so they might just come in the wrong order. And now, again, under smoothness, which you need because of first price unknown evaluation, the regret will be bounded by the sum of regrets of these two algorithms, and you can prove that you get an optimal rate, which t to the 2/3. Okay, so this was a nice solution because these problems somehow are modular in the sense that you can combine solutions for previous settings to solve different settings, like in this case. And this is a kind of easy observation. Oh, you can actually do a bid-ask pair by running first price auctions and posted price auctions. But as far as I know, this observation was never made before, and this is crucial to do this regret, to bound this regret, and we actually get an optimal rate here. Okay, I have a last example, but maybe I will do it very quickly. And this is bilateral trade. This is, so we'll go just in very quickly. This is like Uber. So you are running Uber, and there's someone who wants the ride and someone who's selling a ride. So a driver and some passenger, and they have private valuations. So you want Uber will post a price to both agents, the rider and the driver. And if they are both happy, so if the price you post is bigger than the seller price, so the seller will gain at least as much. The minimum, the seller's price is the minimum price at which I'm offering the ride. If PT is bigger, then you're fine. And if PT is smaller than BT, which is the largest, price at which the rider is willing to pay the ride, then the trade happens. And then we can bound the gain from trade, which is the social welfare, which is the sum of the revenue of the buyer and the seller. And this is the quantity that we want to maximize. And the function is super bad. It's not Lipschitz, and it doesn't have any of those properties that we had before. So we really need to use smoothing here, and I will go over things. So you need the smoothing, and there are a few other tricks here that have to be done. I'm just skipping those. But then you can prove a bound on the regret. You have exploration cost, and you have a bound on the variance. And at the end of the day, if you put everything together, you get this bound. So sigma is because of the smoothness, and this is your rate, which is the worst that you saw before. So let me conclude with, and this is again is tight. So let me conclude with some slide which is a general view of everything. So we saw 4 applications: second price, posted price, first price, and bilateral trade. There's many more, but we don't see. So the first two were Lipschitz. The revenue function was Lipschitz. So you can directly discretize, no problem. The 2 remaining ones are not Lipschitz, so you have to use smoothness in order to be able to do something. And then you have, some of them have one-sided observability and some others don't. So in the sweetest case, you have Lipschitzness and one-sided observability. The variance is nicely bounded in terms of the grid size, and you get a full info rate. Now, if you are giving up on one-sided observability, but you retain Lipschitzness, then the variance will be slightly worse, 1 over epsilon. Well, will be exponentially worse, 1 over epsilon instead of log 1 over epsilon. and your rate becomes t to the 2/3 instead of square root of t. But now, if you don't have Lipschitzness, but you have one-sided observability, then you somehow use the smoothness to recover the smiley face over here. So by smoothness, you make it Lipschitz in expectation, and you can recover the rate over here. Okay, so the variance become actually bounded by constant, and you recover the square root of t rate. And in the worst possible case, nothing, you don't have Lipschitzness, you don't have one-sided observability, so you have to introduce smoothness. But now the bound on the variance is the worst of all, 1 over epsilon squared, and then you get correspondingly the worst rate, which is 2 to 3/4. And all these rates are tight up to logarithmic factors. So yeah, that's it. We don't quite have a general theory here. We can use partial monitoring, as it was mentioned before in the first question. But partial monitoring won't be able to recover all these rates so nicely, and won't be able to deal with all these smoothness tricks that we have used. Okay, so partial monitoring is too general in a sense. Here we are trying to understand what is the interplay, as I said at the beginning, between all these structural properties and the optimal rates. And this is really, we are building this from bottom up, and we are trying to abstract the general principles, because the goal here is that you give me a problem, I just look at the few features of the problem. What is the decision set? What is the revenue function? What are the properties of the revenue functions? What are the properties of the feedback? Then I know exactly what is the estimator to use, and I know that I will get a certain rate. We are not at the stage yet. We have to build everything ad hoc. But we are starting to see some general picture emerging here, and which is kind of interesting and fascinating to me. Thanks a lot for your attention.
Thank you very much. Thank you very much for the great talk and beautiful insight for this research. So, yeah, question?
Yeah, hello. Thanks a lot for your great talk. And I have some questions about the first price and bilateral trades. And by the way, it reminds me of the real auctions or in real applications, as you mentioned, Ubers. Okay.
Yeah.
And it reminds me of some applications with context. For example, in real world auctions, auction companies usually introduce some context or real informations about the product, which gives you some valuation or some kind of information-ish thing. And also for Uber, they have the companies usually have some kind of information they can use, like GPS or airport arrival time or something like that. So is there any research with that kind of context?
So, definitely true, absolutely. Everything here is non-contextual, but in practice, you will have context always. That's absolutely true. Some of these works have been generalized to account for context. There's always two things. Context could be some kind of discrete things, maybe arranged in a hierarchical way, so that you have some rougher information. Maybe in some cases contexts are arranged on a tree, and then you can decide to look at the finer information or more or rougher information. But in the general case, if your context is a vector in some linear space, then you need to have some modeling assumption to decide how the revenue is going to be parameterized by the context. Okay, and it becomes a different thing. Sometimes, often you need the stochastic assumptions, and there have been some of these papers have been generalized to that. But there the picture is even more incomplete. So it's definitely an area where someone can work.
Thank you.
I have a question. So in the last result, you showed the regulated bound T to the 4/3.
3/4.
Yeah, 3/4. Yeah, it's are there any reasonable assumption which makes the problem easier?
Yeah, you can make. I think. If you make stochastic assumptions, for instance, in the Uber example, you may assume easily that the two valuations for the two agents are independent. They are stochastic independent. Then you can get a better rate. Here, the theme of the talk was like everything is adversarial. We will smooth in certain cases. But if you really have IID independent, which is not captured by smoothing, because smoothing is always joint, then you get better rates. This is true. So we have one of the papers in the bilateral case has all the stochastic rates. So you see a little bit how things get better as you add the stochastic assumptions to the model. That's definitely true. Yeah.
Okay, thank you.
A question from the floor?
So thank you very much for the very interesting talk. So in your talk, the regret is the regret with respect to the fixed best action. But so it makes sense to me if we consider, for example, the example of the auctions. But so in your talk, you also considered, for example, the problem market makings. And so yeah, to me the considering regret with respect to the fixed price or something for the market making is somewhat unnatural. And so do you think that, for example, if we do some contextualization, so this problem can be solved, or we need some another definition of regret?
No, we can. You're totally right. Somehow, regret is like the non-stochastic setting is somehow addressing, if you intuitively, is addressing non-stationarity. Say, oh, I don't know, my process is non-stationary, so I don't know what is the right stochastic assumption, so I will use adversarial assumptions. But then you're still competing against a stationary decision. So yeah, the right notion would be a dynamic regret. So great. So basically you have two directions. You have the contextual case and the dynamic case. So you can actually work in both things. So you can do, typically in the contextual case, you may compete against the best decision for that context, which gives you a non-stationary benchmark. So yes, absolutely. Or you can do dynamic regret in the non-contextual case, in which you're competing against a sequence of best prices, and then you have some kind of penalization, like the path length in your regret. See, these all things are definitely worth exploring. There are not dynamic regret. I don't know anything about dynamic regret in these problems. It might be easy. It might be very complicated. I have no idea. So yeah, it's all open.
So in any case, do you think that which direction would be more the practical?
Okay, the most practical direction is contextual.
Yes, thank you very much.
But dynamic regret is, I think, is interesting because it's challenging algorithmically, and yeah, I don't know how dynamic, because it's something that when you study regret is a standard thing. Okay, I've done static regret, and now let's see dynamic regret. So yeah, it's also interesting, but in a practical sense, the contextual is definitely the first thing to do.
Thank you very much.
Actually, we have 4 questions from online participants, but due to the time constraint, so let's close this session. So
okay.
Let's thank Nicolò again. Thank you for a great talk.
Thank you for having me here. This talk is about a new combinatorial
optimization problem motivated from communication engineering problems. Okay, this is the joint work with Shuta Kajiwara, Sherif Hashima, and Eiji Takimoto. The preliminary work appeared at a communication engineering conference. Okay, so in a communication engineering area, there are a lot of work using machine learning, say deep learning. But some work also focuses on online optimization problems in communication engineering. And they apply typically bandit algorithms. And as you see here, there are some small example. In a channel selection problem, you have a lot of channel options, and then each channel can be viewed as an arm. Then you can apply bandit problem algorithm. And also, if we think of using UAVs, that is drones, to make a temporary wireless network in a disaster area, then which place to the drone should go can be viewed as arms. So there are some, growing applications on using bandits to communication engineering problems. Well, online optimization techniques can contribute to communication engineering because many tasks need to be done online. So I think communication engineering, this is a really good application of online learning. And you also need a robustness to changing environments. So that's how maybe online optimization techniques help. Okay. Now, let me briefly explain the background. Necessity of, well, maybe you don't know, but recently 5G or 6G wireless communication network have been being developed. And it's basically an infrastructure with a higher throughput and capacity. And the systems can use higher frequency waves than Wi-Fi. So, however, the weakness is that it's very vulnerable to obstacles. So, as you see in the figure, standard Wi-Fi can go beyond the walls or obstacles. However, if we use 5G or 6G, such as millimeter wave or light, then this wave cannot go beyond human or obstacles. So that's the problem they need to solve. Okay. Configurable intelligent surface, which I call RIS here, or it's also called intelligent reflective surface, IRS. Here, this is in this picture. It's a big surface consisting of multiple reflective units, and each reflective unit can reflect the signal, a 5G or 6G signal, and control their angles and strengths. So by using this, you can avoid obstacles, and by using and it deflects the signal and to the users. Okay. Okay. So this is a maybe promising infrastructure for communication engineering people. Then related work was done by Asif et al. They considered a network formed by RIS. As you see, if we put multiple RIS and construct a network, we can avoid obstacles and send the signal to the user. by using this network. However, this advantage of this setting is that relaying signal with this weakens the strength of waves. And also, this is due to by distance or weather or moving obstacles suddenly coming to this in this area and so forth. So we want to find paths maximizing the strength of received signal to the user. Okay. Oh, yeah. And then Asif et al. Consider the following optimization problem to the leaf network optimization. So we are given a DAG with single root and leaf, and we are given a decreasing ratio W, which is defined on each edge. So simply put, if we send a signal to somewhere to another place, then the signal will decrease by the strength is decreased by factor W1 and so forth. So, and then we want to find a path from the root to leaf which maximize the product of weights along with it. And here we denote set P is a set of passes from root to leaf. Okay. Okay. This offline problem can be solved by using the standard Dijkstra method. So this problem is tractable. However, this problem setting is not for online problem. So we are given the information of decreasing ratios on each edge. If it's available, it's okay. But basically, it's not suitable for online setting. Okay. So in our work, we formulated a new online problem. Our problem is an adversarial flow information setting for simplicity. And as same, given a DAG with root and leaf, and we consider the following protocol. We have a player and adversary, and player proposes a pass. So at each round T, player proposes a pass PT, and then adversary gives a decreasing ratio WT, which is a decreasing ratio vector on edges. Now, after that, the player receives received power, which is the product of weight along the chosen path PT. Okay. Okay. Now, the goal is to minimize the regret defined as follows. Here, the first term is a cumulative received power of the best fixed path. And the second one is a cumulative received power of a player. Okay, this problem is a bit non-standard in that this is a combinatorial online prediction problem with nonlinear rewards. And also, maybe a closer problem is a standard online shortest or longest path problem. But in that problem, the rewards is additive along edges. So, but in our case, it's multiplicative. So it's quite different. Of course, you could formulate the problem, online problem, in a way that it can be reduced to the standard online shortest path with additive rewards by considering a sum of here. So here we consider the cumulative sum of product, but you could consider product of weight in the path. But if you take a logarithm, then this looks a standard online shortest path or longest path problem. However, this formulation has two issues. First of all, the magnitude of log of weights. This can become minus infinity because the weight can be zero. I will read. So previous rewards affects too much in this formulation. For example, if the reward is zero at some previous trial, then the cumulative reward becomes zero. Maybe that's too much. Okay. Now our contribution can be summarized as follows. First of all, as I mentioned, we formulate a new online problem. And then we show that, unfortunately, the corresponding offline problem is NP hard. However, it can be reformulated as a mixed integer program. So we can solve it in a practical way. And also, as an implication, by using a previous result of Sugara, we could solve the online problem and obtain a low regret guarantee, and using a MIP solver. So the rest of our talk mainly on this first computational issues. Okay. Let me explain the corresponding offline problem. The offline problem we call sum of product longest path problem, SPLP for short. So as in the previous problem, we are given a DAG with single root and leaf. And here we have capital T multiple decreasing ratio vectors, W1 to W capital T. And their output is a path P star, which maximizing the sum of product of weights along the path. And this is an example for capital T equals 2. So here, the red weights correspond to the weights on the W1, the weights on the first day, and the blue one corresponds to the weights on the second day, W2. So as in this example, the optimal path corresponds to this red one because this sum of product is highest. Okay. Now, we will briefly show the NP hardness of SPLP. This reduction is from the known NP hard problem to mean SAT. So what's 2 mean SAT? 2 mean SAT is here we show a decision problem version. So we're given a 2CNF conjunctive normal formula with at most 2 literals in each clause. So here is the example. So we have 3 clauses, and in each clause we have at most 2 literals here, as you see. And the output is a yes/no answer. If there's an assignment on n Boolean variables, and for which less than k clause satisfied, then answer yes, otherwise no. Then for example, in this example, when k equals 1, then the answer is yes. And the certificate is A equals 0, 1, 1, 0, 0, and so forth. And Kohei et al. Shows that this problem is NP complete. Now I will show reduction from 2 mean sat to SP-LP. Okay. Now we're given input to CNF, and then from this we construct a DAG like this. So each node corresponds to a Boolean variable, and the structure is like this. And maybe for each node, there's 2 edges going from it, and each edge corresponds to assignment to the variable. So as you see, each assignment A corresponds to a path PA. So let's say if this is 0, 1, oops, and 1 and so forth. Okay, now we specify weights, decreasing weights like this. It's a bit cumbersome, but if the point is that we can set weights so that the following relationship holds. That is, for assignment A, if the clause CT is satisfied, if and only if for the path corresponding PA, corresponding to the assignment A, the weight, the product of weights is along the path is 0, and vice versa. Actually, we can implement the weight so that this property holds. Okay, now by using this property, the implication is that T minus, so we sum up this inequality for capital T rounds, and we get this relationship. So by solving the left problem, then this corresponds to the SP-LP. So finding the best path, maximizing the sum of product. And this is correspond to the finding the assignment, minimizing the satisfied clauses. So if we have a polynomial time algorithm for SP-LP, then it implies a polynomial time algorithm for 2 mean sat as well. So that's the proof. Okay. So that's bad news, but at the same time, we have a MIP formulation. Okay, here's initial formulation. As you see, it's nonlinear optimization at a glance. So the first place, we have here, this is path P, but so P is a 0-1 vector over edges. So it can be rewritten like this. So, and here the constraint that the P forms a path. Yes, but it looks still complicated. Now, first of all, let me investigate a path constraint. This is a very standard part in a combinatorial online optimization. So 0 vector P is a path, and if and only if this condition holds. This is called flow constraint. That is, so focusing on a particular node V, and then sum of PE1 plus PE2 equals to sum of PE3 to PE4. So the incoming volume and the outgoing volume is the same, and it's 1. Plus, if P is a 0-1 vector, this satisfies the path constraint over the DAG. So that's easy. Another one is a bit complicated, which we call received power constraints. Here, we introduce a new variable, STV. This represents a received power on node V at round T. Okay. Now, the objective becomes simpler using this new variable. So the final received power to the user corresponds to the ST leaf. So the objective becomes sum of ST leaf over capital T trials. Now the objective becomes linear. That's good. But provided that the following constraint has to be met. Here, this is a linear, not bilinear equations. There are two variables here, P, E, and ST, E, U. Oh, sorry, I haven't mentioned it, but here's the, oh, yes, I have to explain this. So with this notation here, E dot U and E dot V are introduced. This means HE starts from node E dot U and towards node E dot V. And this is a notation. Okay, let me explain with this example. So here we have 3 nodes, STE E1 dot U and STV and STE2 dot U. And the coming signal from E here is WTE1 times PE1 times STE1 dot U plus, and the other one is WTE2 PE2 times STE dot U. And this equals to STB. Okay. Well, this constraint is not linear, so our problem is not MIP yet. But with simple technique can make it linear. So we introduce first a new variable, ZTE, satisfying this, this relationship. So ZTE basically represents PTE times ST E dot U. And this is satisfied as long as these inequalities are met. Basically, the first linear constraint represents if PE equals 0, then ZTE is 0. And if the second one means PE equals 1, then ZTE equals ST dot U. This is a standard technique of MIP literature, but note that this does not hold for relaxed, non-relaxed continuous PE. Okay. Then we get linear constraints only. And now, oops. The final MIP problem is as follows, with a linear objective with new variables and with flow constraints and received power constraints. And there are these many variables and constraints. Okay. Now, let's go back to the online problem. Online problem can be solved using the previous work of Sugara of follow the perturbed reader. This is another standard algorithm by using offline solver to solve online regret minimization problem. And Sugara extended the standard FPL for linear reward or loss to Lipschitz nonlinear reward or loss functions. So, and in particular, our reward is our one Lipschitz with respect to one norm. This is why, because our reward function, this distance is less than 1. And also, for any different path P and P prime, the one norm difference is bigger than 1. So the reward function is one Lipschitz. So we can apply Sugara's work. And we note that the FPL problem, so it's output the path maximizing the cumulative path of accumulating sum of product of weights plus some linear term introduced by random vector sigma t. And the green objective is still a mixed integer program. So we can solve this problem using a MIP solver. Okay. And as a consequence, we get the following result, regret bound, directly from Sugara's result. And this is experimental result. We considered a synthetic example, and we formed two weights. One is a random one, and one is adversarial to follow the leader. We tried follow perturbed leader and follow the leader, and which is a version of FPL without perturbation. Okay. And as you see, for random weights, the green one, follow the leader, is better. We haven't proved the regret bound for follow the leader in a stochastic environment, but it's somehow expected result. And for adversarial weights, as you see, follow the leader become worse, and follow the perturbed leader performs slightly better. Okay, now let's summarize. We formulated a new combinatorial optimization problem motivated by a Leith network. And there are a lot of open problems for theory people. First of all, we don't know any regret bound for stochastic environments. As also, we don't know any bounded extensions. And especially in our work, we don't explicitly use a MIP property. The problem can be formed as a mixed integer program, where the objective is linear, but we don't exploit this fact to obtain a regret bound. But maybe this property can be useful for designing bounded algorithm, but we don't know how to use it. Thank you very much.
Thank you for the talk. So yeah, is there some quick questions or comments? Yeah, so yeah, I'd like to ask the time scale required for this problem. So now you are considering some communication problems. So yeah, in this problem, so we need to, for example, make a decision, for example, real time or once a day or once an hour. Or, so is there some answer?
Well, maybe it depends on the maybe concrete problem, but maybe if capital T is large, then it takes more time, even with MIP solver. So maybe, yeah, the time trial could be maybe, for example, day.
So you mean that so far the how long does it take to solve the MIP problem?
Maybe for small network, it can be solved very efficiently. Mm-hmm. So it depends on the concrete problem.
I see. Thank you very much.
Thank you.
Is there any other questions? Okay, so now the time is already over. So let's go to the next talk. So thank you again.
Hello, and thanks a lot for once again for giving me this great opportunity. And since it's almost lunchtime, I will try to finish it as quick as possible. In today's talk, we will mainly talk about exploring exploration strategies in reinforcement learning. And I'd like to briefly share how I have approached finding my research topics on explorations, mainly for researchers who are new to this field. I assume that most of you here are quite familiar with the concept of reinforcement learning, but to briefly recap, reinforcement learning is a technique that trains an agent to make decisions. There are multiple applications like autonomous driving, robotics, gaming agents like AlphaGo, recommendation system, and large language models like ChatGPT. So one of the main theoretical concerns for the efficiency of reinforcement learning is called exploration versus exploitation dilemma. So one can describe this dilemma by using one can illustrate this dilemma by deciding where to go for lunch. So we always want to have the most satisfying meal as possible. And to do so, we constantly face a choice whether to exploit your information so that using your known information to minimize the risk of your lunch happiness and visit the restaurant that you are familiar with, or do exploration so that you visit a newly opened restaurant to have a chance to improve your future happiness. Multi-armed bandit, which is my main research topic, is a subcategory of RL which deals with mainly on this exploration versus exploitation dilemma. So to explain this, many researchers use the example of casino problem. So suppose that you entered a casino and you were so lucky that you won 1,000 chances to pull slot machines for free. But unfortunately, this is your first time visiting this casino, so you don't have enough information about which slot machine is the best one for your ultimate profit. So you have to use your chances wisely. So you have to spend some of your samples to explore how slot machines behave. And when you have enough information, you will use the rest of your chance for exploitation. So based on your knowledge, you will play the empirically best slot machine to earn the most. That is basically the problem. That basically describes the problem of multi-armed bandit. And this is a formal definition of bandit to briefly recap. So for each time step t, the learning agent chooses an action AT from a given set of k arms. And he or she observes a reward RT, which is a noisy observation of the unknown reward of the chosen action. And in this problem, we assume that the mean of each slot machine, mu1 to mu_k, are unknown. So, and in bandits, the main objective is, as usual, to minimize the regret or maximize the reward as much as possible. So this is a brief recap about what are bandits and what is the bandit problem and what is the reinforcement learning. And today, as I said, like exploration versus exploitation is a main strategy or main dilemma or main theoretical concern in bandits. And especially exploration is mainly the focus of the research. So to start with thinking about exploration strategy, I'd like to introduce two sample cases of mine to help you understand how to begin your research. First is how to explore. So it basically tells you how should you make a smart strategy to collect samples efficiently. And second is about when to stop. So how much information is enough for your exploration and when to stop, and how should you start exploration as early as possible. And actually, these two are the main
ingredients of exploration, and for each part of exploration, I'd like to explain my experiences. So first topic is about how to explore, and I will explain it using my papers about sparse linear bandits and low-rank bandits, which are published in NeurIPS 2022 and ICML 2024. These are joint works with Kyoungseok and Jang in University of Arizona. So what I mainly want to emphasize in this section is that the approaches commonly used in traditional data science may not directly apply to reinforcement learning. That's what I want to say in this section. And so it's worth taking a closer look at how things can differ in reinforcement learning. So in traditional data science, we assume that data is given from someone, and which means that the learning agent has no control over the data distribution. It seems like a bad thing because you don't have enough control, but actually it makes your objective a little bit simpler. So what you have to do is do your best to get the best prediction about the environment as much as possible. That is your objective. On the other hand, the main power and main problem of the reinforcement learning is that your decision is now your data. So actually your decision affects your data distribution. It looks like great because you have some kind of control over your data set. But unfortunately, your poor decisions might corrupt some of the important properties in data science, such as independence or something like that. So which means that it is good that you have some power, but you have to use that power carefully to make a proper prediction and make a smart decision for your future profit. And in this sense, I will explain how the traditional data science and reinforcement learning could be different. And in this section, I will mainly talk about it using the sparse linear bandit setting, where for each time step t, the learning agent chooses an action AT from a subset of d-dimensional space and observes a reward RT, which is a noisy reward, and its mean it can be represented as an inner product between an unknown d-dimensional sparse vector theta star and your chosen action AT. And the objective is to minimize the regret. And so if you are familiar with machine learning course and some linear regression, some of you might think about a field standard prediction method called lasso in this problem. So to briefly explain what lasso is, when you have enough data, A1, R1 to AN, Rn, and when you know the hidden parameter is sparse, it is well known that the lasso is a field standard for sparse linear regression. And lasso is basically a least square regression with L1 regularizer. But the main point is it also true for reinforcement learning? This is my main technical challenge in sparse linear bandit problem. And to explain why it could be a problem, I'd like to disassemble the process of reinforcement learning into these three parts. First is exploration stage, where the learning agent tries to collect data as much as possible to understand the environment. And after that, the learning agent will estimate how environment behaves. And after that, when the learning agents have enough confidence, then he or she will try to exploit his or her information as much as possible to get the maximum profit. This is, according to my understanding, three basic phases of reinforcement learning. So if you use lasso, it means that you will fix your estimation method by lasso, right? It looks great, but the problem is that the learner in reinforcement learning is not just responsible for only for estimation, but also responsible for collecting data set. And why this can be a problem? The problem arises in the theoretical analysis of lasso. This can be seen as the estimation guarantee of lasso can be written as follows. So the lasso estimator, the L1 norm between lasso estimator versus the true parameter can be bounded by inverse square root of the number of sample, which is written as n, and this error bound is also governed by a arm set geometry dependent constant called compatibility constant. This constant can be seen as a kind of minimum eigenvalue ish thing, but unfortunately, it is not easy to compute efficiently. And in particular, nothing is yet known about the optimal experimental design for lasso over a fixed set of arms. So in short, it is hard to compute best exploration plan for lasso, which means that you have to use some kind of alternative for your experimental design. So researchers usually used maximizing the minimum eigenvalue, some kind of d-optimality or g-optimality thing to optimize, get some error guarantee of lasso. But it turns out they are usually quite inefficient because theoretically the minimum eigenvalue and the compatibility constants are quite far apart. So which means that if you choose lasso as your estimation method, it means that you cannot have lasso optimal exploration to optimize your future reinforcement learning process. So this is the point where I started doubting. And my conclusion is, what about not using lasso in sparse linear regression? So our research team tried to introduce a new type of sparse linear regression, which is accurate and has a computationally efficient exploration plan. And I will not explain about the technical details for too much, but basically this new estimation method, we call it as sparse, mainly uses ordinary least square, but with some kind of thresholding. So basically, it first compute ordinary least square and check the magnitude of each coordinate. And if it is not large enough, then we will zeroing out all those small enough coordinates. That is our main approach. And there are many other techniques included, such as one sample estimator, robust estimator, heavy tail concentration inequality, and so on. But basically, this is the main skeleton of our algorithm. And instead of lambda mean based minimum eigenvalue based approach that lasso users have used, we introduced a new experimental design for our own estimation method. And it turns out, as you can see, ordinary least square are much closer to minimum eigenvalue than the compatibility constant. It turns out that we can compute the exploration plan much efficiently by using convex optimization. And also, our algorithm achieved a proper experimental results. But not only that, we proved that our algorithm achieves minimax optimality in high-dimensional sparse linear banded problem. So which means that there is no more improvement possible in kind of theory. And this was our contribution in NeurIPS 2022. And also we found out we can apply this idea to low-rank bandit, which is quite similar to sparse linear banded problem, but the reward can be represented as the trace regression, kind of vectorized inner product between the hidden matrix parameter theta star and your chosen matrix AT plus some noise. This is the extension of the low rank bandit. And one might notice that there are many similarities between sparse linear bandit versus low rank bandits, such as sparsity can be interpreted as lower rank of the low rank matrix. And lasso is the regression method, lasso is quite similar to nuclear norm regularized least square, which is also commonly used in low rank bandits. And they shared almost the same problem. And lastly, we introduced new algorithm called low pavart for low rank bandit algorithm. So these are our first. This is the end of the first section. And basically what I wanted to tell you is that start doubting about the traditional data science approach. Okay, these are some details, but I will skip for now. And the second section is about when to stop. So to explain this, I will use the best arm identification problem that we introduced in NeurIFS 2024. And this is a joint work with Junpei Komiyama and Yamazaki Kazutoshi. So first, I will briefly introduce what best arm identification is, especially in this problem. In this section, we will focus on fixed confidence setting. So for each time step t equal to 1 to some stopping time tau, the agent can choose an action at in an action set k, as many other bandit problems do, and observes a reward rt, which is, again, a noisy observation of the unknown mean mu at. These are quite similar to our traditional bandit problem, but the main point is that the learning agent can decide whether to continue or stop this game. And when the learning agent is confident enough about his or her information, he can stop sampling and make his final decision or recommendation J. And that recommendation, we hope that recommendation J be the best arm among mu1 to mu k. And the objective is to minimize the number of samples required for identifying the best arm. But we also hope that that recommendation is exactly the same as actual best arm with high probability. So this is the basic of best arm identification. And there are many other applications for this best arm identification, such as clinical trials. So I will skip it for now. And the main contribution in this section is the first result on fixed confidence best arm identification in the Bayesian setting. So the fixed confidence best arm identification has been studied for a long time, and especially around 2016, Emily Kaufman and Daniel Russo and many other researchers found out an optimal strategy for fixed confidence best arm identification in the frequentist setting. So on the other hand, in the Bayesian setting, little has been known about this environment. And to explain what the Bayesian setting is, everything else are the same, but the only difference is that when before the game starts, the unknown mean mu1 to mu k are drawn from a known prior distribution H, which means that the learning agent now can exploit some kind of prior information about the environment. So it looks like this problem is easier than the previous traditional best arm identification problem in frequentist setting. But it turns out that we discovered that all known frequentist-based algorithms have expected stopping time equal to diverges in the Bayesian setting, unlike the fact that they were optimal in the frequentist setting. So to explain this phenomenon, it is mainly because the correct FCBA algorithm, which is basically in the frequentist setting, they never stopped identification until they are certain about their decision. So to explain what it means, so in the first figure, as you can easily guess, when two or more arms are in a narrow gap, you need more samples to identify which one is the best. On the other hand, when there is enough size of gap, usually it is much easier to identify which one is the best. So there are multiple cases possible in the Bayesian setting because your instance mu1 to mu k are drawn from a prior distribution, right? But it turns out that the growth of the number of samples required for identification when the gap became narrower and narrower, the growth of the number of samples is much faster than the shrink of the probability of the narrow gap event. So when you compute the expected number of samples for FCBA problem in Bayesian setting, it turns out it usually diverges, which means that if you give any algorithm that works in frequentist setting in a proper manner, it will diverge. So this is one thing that we proved. And naturally, the solution is that since all the problem happened because the growth of the number of sample is much faster than the shrink of the probability of narrow gap event, we have to stop identification when the estimation gap is too narrow. And we know that narrow gap event will happen rarely. So if you think about drawing two Gaussian distribution, it rarely happens when those two are equal or almost equal, only different phi epsilon. It happens very rarely. So we can give up in that case, but except for that case, we will try our best to identify which one is the best. So this kind of approach is possible because we are in the Bayesian setting. So basically, these figures show what this means. So in frequency setting, in all instances, algorithm should satisfy the error probability should be smaller than or equal to delta. On the other hand, in Bayesian setting, the prior distribution over problem instance is given. And what you have to satisfy is that the total area under your error probability curve is less than or equal to delta. That is the condition that you should satisfy in the Bayesian setting. So you can exploit this property to find out appropriate moment to stop your identification. So to do that, some parts are being cut out, but actually we introduced a new algorithm based on successive elimination. So except for this red box, everything else is almost the same as the traditional successive elimination algorithm. But in this red box, we stop identification when the estimated gap is smaller than a certain threshold delta, which means that we are quite certain that we are in a narrow gap situation. And in this case, you should give up your identification sampling anymore and try to randomly pick which one is best in your active set. So these are some contributions that we discovered that the traditional frequentist delta correct FCBA algorithms will fail in the Bayesian setting, and devised an algorithm with early stopping and proved that our algorithm, I didn't introduce some details about lower bound, and we proved that this algorithm is quite optimal up to logarithmic terms by proving a lower bound. So this is about the second section. And the thing that I want to say is that what I want to say is that you don't need to change too much about algorithm. If you are well aware about when to stop, that is enough for your future research. And here's the conclusion. So reinforcement learning, in theoretical perspective, reinforcement learning can be represented as an exploration versus exploitation dilemma. And to explore exploration, there are two factors of exploration that you can focus on. First is how to explore. And to explore how to explore, what you have to do is start adopting one possible approach for exploring exploration strategy is to start adopting about traditional data science-based approach. And the second is when to stop, which is important for your efficient exploration. And okay, yeah, so this is the end of the presentation, and thank you for listening.
Thank you for the talk. So is there any questions?
Yes.
Thank you for great talks. I'm curious about second talk. So second part. So you mentioned about the extension for low rank matrix bandit to remove the minimum eigenvalue of VT gram matrix. So, but this
here.
Maybe next slide.
Next slide.
Okay. I'm when you even the low rank matrix setting, it can be done computationally efficiently, or you might involve the E-optimal design, which is NP hard. Or
it turns out that we can also compute efficiently for our new estimation method, low pop art. And actually, most of the approaches are quite similar to what we did in pop art approach. It is also kind of, so actually, as you know, low rank matrix is a little bit more complicated than the structure of sparse linear structure. So there are a little bit more, how should I say, technical details or theoretical abstraction, but actually the bases are the same. So basically, there exists a computationally efficient experimental design, which is kind of similar to minimum eigenvalue based approach, but a little bit more complicated, but still computationally efficient, and everything is good. Yeah.
Great. Thank you.
Okay, thank you.
Any other questions? Yeah, I also have a question regarding this part. So regarding the sparse setting, so you handcrafted the estimator. So it is surprising that your algorithm is also good from the viewpoint of the estimator. So yeah, can you show the?
Here.
So it is hard to believe that some handcrafted estimator is better than the Lasso in general. So is there some trick or some sacrifice compared with the typical Lasso estimator?
Yeah, that is a good question. So like basically our algorithm assumes, so especially first about bandits, as I said, like in reinforcement learning, first about the problem setting, we assumed that we are in high dimensional setting when D is comparably large compared to number of samples. So in this case, people usually use explore then commit based strategy, as you can see from this figure. And in explore then commit, the size of the exploration phase is very important, right? But it is quite a conservative approach. And when there's a mismatch between the exploration plan and estimation method, it naturally incurs a excessively large amount of exploration phase. And for the first one, the estimation error. So this is not only Lasso, but basically this seeming Lasso means that you are using minimum eigenvalue based exploration and Lasso. So if you are saying that if one uses same data set, then you are quite right. Lasso is very efficient. But this means that this picture shows that this first prefix represents what kind of exploration plan you have used, and the second one represents what kind of estimation method you used. And because of the mismatch, as you can see, that Lasso shows quite a bit of inefficiency in the real result in high dimensional setting. That's what I wanted to explain.
So it depends on the data collecting process.
Exactly. It is not the problem of estimator itself, but mainly the problem caused from the exploration phase and data collection process.
I see. Thank you very much. So is there any other quick questions? Okay, so yeah, now it's time to close the section. So thank you again.
Thank you.